Welcome back. So we've been working on designing a vacuum. We have built most of the functional components. We've built a fan, we've built a reservoir, we've built a filter. All of these are individual components. We really haven't done anything to put them together. But before we really start to put them together, which is this process, turn them into a functional unit, a system, we have one last functional component we need to choose. And what we're going to do basically, once we have designed all four of these, we're going to find a way to orient all of them and then build the rest of the system around that. It's a very iterative process. You end up moving things, you end up changing things, you end up adjusting things, but it would be nice to have overall a layout of here's what I want prior to getting involved in here's how they're all connected. This is a fairly complex system, so bear with me here. And this time we're going to talk about, we've already finished the fan, we've already finished the dust reservoir, and the filter design. At this point we're going to be looking at the motor. So before we really start looking at a motor, we're going to do our research. So again, I'm a big fan of jump online, use your resources, find ways to see what's new in Chrome, but find ways to dentists near me. I cracked my tooth yesterday, so yep, my Google search is very interesting. So anyways, here what I'm going to be doing is I'm going to be looking up just brushless DC motors. Okay, now why am I picking a brushless DC motor? Brushless DC motors tend to be a little bit more powerful, a little bit more expensive, but also a little bit lighter than traditional brushed DC motors. They also have a longer longevity, but being a little bit more expensive, it depends on where you get. So if you just start searching up brushless DC motors, you see a bunch of ads. You're going to see some, what is a brushless DC motor? If you really want to learn about that, that's great. And as you go through this, it's like, okay, there's tons of different sites. There's tons of different types of electric motors, brushless electric motors. How do we pick one? Well, it comes down to this. And this is something you're going to be learning about in our engineering program moving forward. But when it comes to choosing a motor design, you need to select a motor that is that has a voltage that you want, a current rating that you want, basically a power output that you want. For most vacuums that I would see, like how much power does a vacuum consume? Okay, so we just look that up quick. It says between 500 and 3,000 watts. So a best-selling model will use around 1,400 watts. So that's about 2 horsepower. I mean, that's a lot. No, that tends to be for a more upright vacuum, something that will have a brush roller in the front. Since I'm just having the vacuum piece itself, I'm probably going to be closer to the 500 to 800 watt range. So really that's what I'm looking at, is I want a motor that's going to be within about 500 to 800 watts. You may go look at a similar vacuum cleaner and say that's around what you want. But I'm going to take that number that's important. And the second number is, now I need to go look at DC motors, and I need to go look for an 800 watt brushless DC motor. Okay, so I type that in. I'm going to get a couple of different results. Here's a 60 volt, 800 watt, 1800 RPM brushless DC motor. I can go click into this. We can go down this rabbit hole, do some research, search at it. Yeah, okay, great. Operates off of 60 DC volts, 60, which is incredible. Maybe I am going to go closer to the 500 to 400 watt range, because this is insane. Yeah, we will not do that. So mine's going to be a hand vacuum. We're going to do we're going to try to see what a 400 watt has. And just because, since mine is going to use it's going to have to be portable. I'm planning on doing it with having a battery on board. Anytime you usually have an appliance battery, it's somewhere between 12 to 24 volts. You can have less than that, but usually more than that. The batteries start to get pretty extreme. I've seen some vehicles that have 72 volt battery systems, but I don't really want that in something I'm carrying around. That's a lot of battery to just have as a dead weight. So rather than use a 72 volt, I'm going to be looking for a 24 volt, 400 watt brushless DC motors. So I can click on a first ad I see. Nanotech is a company I've seen before. ATO I have not seen before. McMaster is a company that I'm also really used to working with. Here I will want something that is fairly high torque for a reason. You know what, I'm going to try going in and looking at McMaster Electric. Why not? It's a Belmont company. So this is what the motor looks like by itself. Now here, just looking at the specs of what this motor looks like, that looks a lot like what my fan already has. So the nice piece about having that is, with this being fairly compact, it would mesh really well with my my current existing fan blade. Now here, if you want to start talking about performance curves, these performance curves are really interesting. Here this shows that your torque down here, depending on the model, if I wanted to go with a 400 watt model, 400 watt model is, oh no, the power is the blue line. Huh, that's interesting. I wonder how it, okay, all right. So at 500 watts, you have this amount of torque and you have this amount of speed. This is your maximum power output here. Your efficiency, your maximum efficiency actually happens at a very low torque value. So you wanted to operate at a very low torque value. Problem is, your power level is pretty low at that point. You're looking at maybe 180 watts of power there. So depends on what you want here. As a designer, you're looking at which one of these matters most. So here it'll tell you at max efficiency, here's your speed, here's your current, here's your torque, here's your efficiency. It's just all these things. All of this is really good to know. I'm going to go ahead and take this brushless DC motor, and you'll notice this does have some specifications to it. I can't really see it because I'm blind. But the outer diameter of this motor is 119. Looks like there's a 9 millimeter bridge right there. You have that long of a lead. Wow, it's really not a lot of information. But this does give me enough that I could probably redraw this in SolidWorks if I needed to. Here's a bunch of the other specifications. So when you're looking up a motor, the piece that you need to have most importantly is this information down here, which gives you your load, your speed, your current, your torque. You need to understand those. Now here I have the ability to pick between these to be able to say, excuse me, all of these are 24 volt batteries. All of them have 71 millimeter lengths, which I would assume would be from here to here, 71 millimeters. Here the power output in watts, we're probably going to want the highest level one, just because. Although it is going to be a little heavier, it is going to have a higher current draw, it's going to have higher speed. These are the shapes of the diagrams. You'll notice that these values over here, it appears what they did for this was they gave these values according to the specific models, and then they just basically showed, here's what you would expect out of the performance. So here, current linearly increases as the torque increases. speed linearly decreases as the torque increases. Your efficiency pretty much decreases as the torque increases, and the power has kind of a parabolic shape. So that's kind of what this shows. You can look up here and find the actual values to plug into some of those numbers and recreate the curves yourself if you really want to. But here I'm going to say, okay, so rated load has current, ooh, snap, 19.8 amps of current, fully loaded. Wow, that is a lot of power. Yikes. That's pretty beefy. We're going to have to find a battery that can handle peak loads around 15 to 20 amps, which that will not be easy. We're going to end up finding a pretty gross battery. Whew. Wow. But you know what? We'll do it. We'll make it work. All right. So I'm going to go with this one. You can always find a better one if you want. But this is the one that I'm going to go with. So what I'm going to try to do is I'm going to try to recreate this drawing exactly in SolidWorks. Okay. Now I will say I am not going to try to recreate all of the screws, those little fun dimensions. I'm going to have to make estimates about the lip size here. I'm going to have to make estimates about the distance between those bolts. Really what you would end up doing is you would buy one of these, or you would ask the company for more detailed specifications on the part. They may actually provide you with CAD drawings themselves, which is likely what would happen. They give you CAD drawings and you say, hey, I want to forge an alliance with you, and you go and raid small kingdoms together or something. But that's what the inquire button here is for, is to get the CAD drawings. They don't usually post them publicly because people can steal your intellectual property that way. So they make you use the inquire button so that if you steal their intellectual property, they know exactly who you are. Fun times. There's an IP address associated with that. I don't want to give them my IP address, which is why I'm just going to make this up myself. So we're going to take this, we're going to try to recreate this, and let's go. Now before we really get started, this is 119 inches in diameter. This is 119 millimeters in diameter, 71 millimeters. I'm an inch guy. I like inches. So I'm going to take 119 divided by 25.4, and that is 4.685 inches, which is really close to the diameter of my fan. So heck yeah, that means that my parts will fit together really well, thankfully. All right, so going back into SolidWorks, I'm going to create a new part. Now, if you made a full model of a motor, what you would end up doing is the motor housing, which has all of the electronic components to it, all the wire, the copper wire, all of the control sensors, that type of thing. That's all one unit, and then you have a shaft that spins independently. You could model it as two parts, a motor realistically, and then you would be able to actually power the motor through. I am not going to be modeling this as two different parts because, you know what, I'm tired. I have a life. At least that's what my mom tells me. So I will not be modeling the entire thing. Instead, I'm just going to be modeling the motor itself and getting a very rough outline of how much the motor looks like. As I've mentioned, an exact model of the motor you could get at least the dimensions for by discussing it with the vendor. They would allow you to have that so that you could put that into your own design and plan for that exact specific model. But I don't care. I'm not going to try, and I don't want them to have my email address, and I don't want to get the spam email for the rest of my life because I looked this up one time during class. No, I'm not salty at all. What are you talking about? And I was going to laugh because I'm talking to myself, but really every one of these videos I record, I'm talking to myself. So we're going with 4.685 inches. There we go. There's the outside exit sketch. Now here, if I go back to my dimensions, this is 71 millimeters. That's the extrusion depth. So 71 divided by 25.4. That is 2. So we'll jump back into this. Go to extrude. And I will do a blind extrusion. 2.795. Now I am going to switch the direction real quick because I want the origin to be up here. I'm going to draw the actual motor axle coming out that direction, and I want this to be at the base of that motor axle. So just a personal preference. All right, gonna draw that motor axle. Putting it at the center. Does it give me a diameter for it? No. That is a diameter of 8 millimeters plus 0 or minus 0.009. That's tolerancing. Basically, when they give you a tolerance like that, the idea is you can expect it is at most absolutely 8 millimeters, not more, but it could be as many as 9 thousandths of an inch of a millimeter less. So that's what tolerancing does. For someone like you or me, that means when we go to fit in a hole, we would fit it in a hole. If we want a regular fit on this, we would get a hole that has 0 at the minimum, but maybe plus 0.009 so that there's a little bit of space so we can slide it on. If you want an interference fit, you would want maybe minus 0.009 as the maximum, and then maybe minus 0.018 as the minimum. So that's kind of how tolerancing works. Here, this is 8 millimeters. We go ahead and throw a dimension on this, and then figure out what is 8 millimeters. It should be 8 divided by 25.4, 0.315. 0.315. A little bit more than 1/4 of an inch. A little bit less than 3/8 of an inch. All right, so there's my motor shaft. I'll exit sketch, see if it gives me a length on this, and the answer to that is no. So, go back to SolidWorks, and I'm going to estimate a length. I'm going to estimate a length of, I don't know, about an inch, maybe. Maybe less. Maybe more. Maybe less. Maybe more. Yeah, I'm going to go with about, I'm going to go with 3/4 of an inch. So this is going to be 0.75. Extrude it that way. And hit enter. Hit yes. Look at it from the side. Does that look like what I have here? And yeah, it actually does. It's really close. Now here, there is a little ridge, a 9 millimeter ridge. It's located about 55 millimeters below the tip of this thing. So what I'm going to do is I'm going to create not a sketch, I'm going to create a plane. And what I'm going to use as a reference is the point that I was given for the measurement, which is this face right here. And it's going to be offset this way by whatever that value was, 55 millimeters. So 55 divided by 25.4, 2.165. So 2.165. Enter. And there's my plane. It's right in the middle of the object. Nice. But it is fully defined. I hit enter. I have that plane still selected. I go into sketch, I draw a sketch. I'm going to zoom into top view, and I'm going to draw a circle. Now this is a ridge. Looking at this, it does not tell me what the diameter of that ridge is really. I mean, I guess that ridge actually is the 119. Oof. Didn't see that. Well, that is that's 119 from here to here. This is less than 119. I don't know what that diameter is, so you know what? I'm just gonna pretend that this is 119. Dang it. Alright, so 119 divided by 25.4. Okay, so I drew a circle, 4.685 inches, and then I'm going to have to go back and adjust my other circle because I got that one wrong. .685. And we're good, and we're good. Now before I go and extrude this, I'm going to go back to my original sketch, and I'm going to say, you know what, we'll make this an inch smaller. This will be 3.685. And then we'll hit exit sketch. The nice thing about SolidWorks, being what it is, you can always adjust. Look, it kind of looks like, oh, I can't say that on YouTube. Uranus. I said it on YouTube. So now I'm going to extrude this part upward. And this one was, the lip distance was 9 millimeters. So 9 divided by 25.4 should be around 3/8 of an inch, a little bit less. 0.354. So here, 0.354. Enter. Hit yes. And there we go. Now, a couple of last minute housekeeping items. There are 4 mounting holes located around the edges here. They are drilled in this flange itself. This is what is used to connect this motor to some kind of a structure. So I need to put in all 4 of those holes. Okay, so I'm going to zoom into top view, go into a sketch, going to draw a sketch on this plane down here. So I click on that face. Going to draw 2 circles. Well, I'm going to draw 1 circle. I'm going to draw a construction line, because I love me some construction lines. Escape out of this. And then, according to this drawing, that is a 4 millimeter hole. So I will go in here and I will find out what 4 millimeters is. 4 divided by 25.4, 0.1575. .1575. Tiny. And then what I probably could do is I could probably just try to center it between these two, which means I need to delete this constraint and move this over so that it's here. Now what I will do is I'm going to click on this line and then control click onto this origin, and I'm going to make them be coincident. So they're pointing at each other. Okay, so that's good. You know what? I'm just going to delete these 2 lines and try again. Dang it, Kale. For construction, it's going to go from this curve to there. Hit escape. I don't want it to be tangent, so I got to delete the tangent. but I'm going to connect it right there. You'll notice that because it's on the midpoint, it is actually connected. It's coincident. However, I can move it up and down. So with that line selected, I go back again and select this one, and I make them coincident, which should fully constrain this line. Oh, I need to set this as horizontal. That's right. And that should fully constrain that line. There we go. Then we'll do another construction line from here up to this point here. I'm going to make this line be vertical. And we're good. We'll do a smart dimension. This piece here. And then we'll say, well, it didn't really give me a dimension, so I'm just going to put it at 0.125, about 1/8 of an inch. Nice. Probably should do a little bit more than that. Maybe 0.1, maybe just 0.2. Okay. A little bit of a gap. We'll hit OK. I will then want to mirror an entity. The entity I would like to mirror is this one. I want to mirror about this. Hit yes. And there we go. I have 2 holes now. Okay, hit exit sketch. Before I do anything, I am going to do an extruded cut. I'm going to have it go through all. So here, through all. Hit yes. Okay, and now all I need to do is just mirror those holes 4 times around, which is what we see here, the 4 mirrored holes around here. So to do that, I do a circular pattern. I still have the cut extrude selected, so it's going to automatically say that's what I want to do. The direction, I have to pick an axis. Here I want it to go about the center. Well, there is a center line there. I just have to go to hide, show, temporary axes. And when I do that, then you'll notice there's an axis there that I can select. Okay, now here I want an equal spacing, but I only want to have 4 instances. So I hit enter, and notice it pops up 4 times. And I hit OK. And that is my motor design, including the motor mounts. Ha. So that's good, because now I can use this anywhere I need to mount it. I will need to make sure that I get appropriate bolts that are the size of these so that I can actually connect the motor, but we'll deal with that later. So start by saving this piece. I'm going to save this as a motor, but that's not the only thing I'm going to do here. Here this is, I'm just going to call it motor, hit enter. But before I really jump out, hit reset. Before I really jump out of here, I need to make sure that I also get the motor number. So here, I'm going to be grabbing this motor number, copying it, going in, changing the name of the motor to include the part number. Okay, but that's not all. Oh shoot, I gotta shut SolidWorks off. Bye. Try again. Or I might have just broke my computer. You never know. But I saved it with the motor part. Something else that I like to do, and something that is good practice, is just come up with a document and then just say parts, numbers, or something. So any part that you're planning on including in your document, keep a way to find it. Okay, so here, I can copy this website. That's one way to find it. So motor specs, copy the website, copy the part number, or here, just screenshot it, print screen, paste. Okay, and here I've got the highlighted one that I want. I could crop it down so it only shows that, but eh. And then I'm also going to go in here and pick the overall design, screenshot that. Basically just giant plagiarism here. But I want to keep this information so that I can take it and use it later. I'll also take a screenshot here that has all of this information, and I'll put it up at the top. So there we go. So now I have chosen my motor specifications. I've picked my motor. I have all the details here saved in this document. I'll hit save, cancel out, go back in here, and I have completely designed my functional components. For the remainder of these videos, we're going to be working on assembling a hose, battery, intake, piping, all of those fun things that really forces this thing to come together. But we will do that